to Unit 3, Recording 2. And in this recording, we are going to talk about the dual nature of the electron. The electron is so very, very small that it acts as a particle and a wave. And so in this video, we will be talking about the wave function of electrons and a little bit about energy in general and electromagnetic energy. And so how do we know that the electron has this dual nature? Well, we know through a famous experiment that we're going to cover here in a minute. And I have a little screen here that, or a little illustration that shows the experiment. And this experiment was conducted by a fellow by the name of Carl Jung. And the name of the experiment is the double slit experiment. And what he did was he took a particle gun. We'll summarize it and then we'll do it more formally and let you take some notes on it. But he took a particle gun and he shot particles at a image or not an image, but a piece of metal with a slit cut in it. And he just had one slit open at first, and he let the particles go through, and he noticed that instead of this picture here, you had a picture of just one image going up and down the slide. And then he opened up the second slit, and again, these aren't electrons, these are particles that he was shooting through, or bits of matter, and it had two images, just like you would expect. But then he switched and he put electrons through this panel, and he opened up one of the slits, and he noticed, just like with the particles, the regular particles, you just had one image. And then when he opened up the second slit, he thought, well, you would get two images on the screen. But what he got was a variety of images. And so from that, he concluded that the electrons were hitting these like a wave. And so he postulated from the experiment that electrons have a wave function. So he shot particles and electrons to a metal plate with two slits. He discovered that when one slit was open, the electrons seemed to behave like a particle. But then when he opened up the second slit, he noticed that they behaved like a wave. And when both slits were open, an interference pattern appeared, and the wave nature of the electron was discovered. And this is a better illustration of that, and how the waves, you expect them to have greater images at the top of the wave and less images at the bottom of the wave, and so forth. And so he noticed this pattern. And this is how come we know that electrons travel or have a particle in a wave-like nature. And a little bit later on, we'll talk about a scientist called Broglie, who actually was able to calculate the wave function of matter. And so what he noticed was that when matter was heavier, it behaved more like a particle, and he could give a number to the wave function that was very, very low. And then as the matter got smaller and smaller and smaller, like an electron, it had a greater wave function. And he did that mathematically. It's pretty interesting. So we glean from this, the better we understand electrons, to better understand electrons, we must understand wave properties. Okay? And so now we're going to talk a little bit about wave properties. And when we do that, we talk about energy, and energy in this electromagnetic spectrum. Energy of all types have wave functions. Wavelength is the length, the distance between any two successive peaks or troughs in a wave. So if you think about that like this, okay, so the distance between here and here, or the distance between here and here, is considered to be a wavelength. And we give these wavelengths a funny symbol, lambda, and it kind of looks like a wave, this lambda symbol, and it looks like that. So I always say it kind of looks like a wave crashing on the beach to give you an idea of what that looks like. Okay. And frequency is the number of waves that pass by any one particular point in a second. And so it's the number of these waves, right, that pass by any one point. And we give that a symbol of nu, which kind of looks like a V with a top on it, like that. And it's not frequency, it's not velocity, but it's frequency. But how I kind of remember it, V for velocity and frequency are very similar. And so, but frequency is the number of waves that pass by any point in a second. And you'll notice here that the units of this are cycles per second. And sometimes they call this hertz. If you think of radio broadcasts, they say it's so many megahertz. So that tells you the frequency of the emission of the radio waves. Meters, here the units for those are meters, or the wavelength, is meters or nanometers. And here we have the electromagnetic spectrum here. And in this electromagnetic spectrum, you have a gambit of energy and frequencies of waves. Let's talk about the visible spectrum here first a little bit. And so we'll talk about this visible spectrum first. And of course the old saying is Roy G. Biv, right? And in our example here, we have the highest energy wavelengths on the left-hand side of our chart and the lower ones on the right. And the same is true of the visible spectrum here. You got red, Roy orange, yellow, green, it's hard to say it backwards, blue, indigo, violet, right? Biv, B-I-V, indigo, violet. And so these are in reverse order of how we learned how to maybe say it in elementary school, Roy G. Biv. The red are longer and less energetic, and the blue, or the indigo and violet, are shorter wavelengths and more energetic. And so the same is true for our electromagnetic spectrum. We've got gamma, X, UV, vis, infrared, microwave, radio wave. Of course, gamma waves are very, very short, very, very energetic, followed by X-rays and ultraviolet rays, infrared rays, microwaves, and radio waves. So these are the shortest. They say 10 to the 11th, 10 to the negative 11th meters. Okay, here in the visible spectrum, we're around 10 to the negative 7 to 10 to the negative 6 meters. And then they get progressively longer here, 10 to the second, 10 to the third for radio waves. The longer the wavelength, the less frequent the cycle, and the lower the energy of the emission. A fellow by the name of Max Planck developed a way of quantifying the relationship between frequency and energy of emissions. And he came up with something called Planck's constant. And Planck's constant is noted by the letter. And so Planck's constant is one of those numbers that we will talk about in more detail later. 6.626 times 10 to the negative 34 joules seconds are the units for that. And he said that energy is equal to H, or Planck's constant, times the frequency. And we will use that to work some problems a little bit later. Max Planck was an interesting fellow. He was a German scientist, and unfortunately he worked for Adolf Hitler in World War II, and he's given the dubious credit of the first one to weaponize chemicals for battlefield use. He used chlorine gas on some rivals on the battlefield, or he was the one that came up with the idea. So not a nice person. Another fellow that was working on this whole thing of energy and wavelength was a fellow by the name of Louis de Broglie, and he was able to come up with a way of quantifying the wave function as related to the mass of the particle. And so what he showed was that mass of the particle, as the mass decreased, the wave function increased. And so, you know, we had the Young experiment that showed electrons traveling as waves, and then we had de Broglie's mathematical relationship here, and you can see the formula here. It said wavelength is equal to Planck's constant divided by mass times the velocity. And it's important to note here that the velocity here is not a frequency, but it's actually a different kind of measurement. It's not wavelengths per second like frequency is. It's actually the movement of the particle itself, or the speed of the, well, it's not speed, it's velocity, which also takes into account direction. When you take physics, you'll go through the whole process of distinguishing between velocity and speed and so forth, but it's the velocity of the particle that's important here. We won't work problems with this one, but it's kind of interesting to note. You can actually take the formulas that we're talking about and Einstein's formula, E is equal to mc squared, and you can combine those to come up with this formula. I'm going to talk about the mathematical relationship between frequency, wavelength, and energy. We already talked about the general relationship. We said that the longer the wavelength, the less frequent the waves, and the less energetic the waves. And then we said that the shorter the wavelength, the more frequent they are and the more energetic. And then we have some mathematical formulas that you can quantify these variables. And the first one that we will talk about is the one on the left here. And we'll talk about C is equal to lambda nu. Remember, lambda is like a wave crashing on a beach. A wave crashing on a beach. And so we call that the wavelength. And then the frequency variable here looks a little bit, frequency and velocity are very similar quantities. So it looks like a V here. And so the frequency is the Greek letter nu. So C is equal to lambda nu. And of course, the thing that relates those here is the speed of light. And that's the thing that we're going to introduce here. It's a constant. It's called, the value is 3.00 times 10 to the 8th meters per second. And there's a scientific law that says nothing can travel faster than the speed of light. And they've been trying to disprove that for many, many years now, and never have quite been able to get something quicker than the speed of light. And then the other formula that we are going to use is, of course, Planck's formula. E is equal to Planck's constant times the frequency, and we'll use that in some example problems as well. Before we get to the problems, we're going to re-emphasize the relationships here. So increase wavelength, decrease the frequency and the energy, and decrease the wavelength, increase the frequency and the energy. And I always think, students think long, lazy waves. The longer the wavelength, the less frequent it is and the less energetic. We are going to work some problems with our formulas. In this first one, it says, what is the frequency and emission of blue light with a wavelength of 4 times 10 to the negative 7 meters? So we're going to solve for frequency. So our mathematical formula is C is equal to lambda nu, or C is equal to the wavelength times the frequency. Here we're solving for our frequency, so we'll multiply through by the reciprocal of 1 over the wavelength to isolate this variable. So wavelength will cancel out, and so we'll end up with C over the wavelength is equal to the frequency. So let's do that. Frequency is equal to c, which is always the speed of light, to the 8th meters seconds. That over 4.00 times 10 to the negative 7 meters. So here meters will cancel out and our answer will be in 1 over s, or hertz. So let's think about our calculation here. Estimate a value and then calculate it. So we say 3/4 would be 0.75. And then when you have exponents, when you're dividing them, you actually subtract them. So it would be 8 minus a minus 7, or 8 plus 7, which would be 15. So my estimate here is 0.75 times 10 to the 15th. And so when you write a number in exponential notation, it needs to be between 1 and 10. And then so we'll make this 7.50 times 10 to the 14th. So I encourage you to plug that into your calculator and double check your answer. In most calculators, they have what they call an exponential notation key, and it's an EE key. So you'll need to learn how to use that when you plug in your numbers. I will kind of write it out here for you using a TI-80, let's see what I got, TI-84 calculator. So when I did that on mine, I'd type in 3, and then I'd hit the second key, and then the comma key, and on the comma key it should have an EE on top of it, like that. And so I'd hit 8, and then I would divide that by 4 times, or 4 second key, EE key, which is a comma key, -7. So try that out and see if that works for you. If not, you might need to refer to your calculator's manual to figure out how to do that. All right, so the second problem is, what is the wavelength of an emission with a frequency of 3.75 times 10 to the 14th? So we're solving this time for wavelength. The wavelength will be c over the frequency. So we got 3.00 times 10 to the 8th meters seconds over 3.75 times 10 to the 14th meters seconds. I'm sorry, 1 over s here this time, 1 over s. So this time seconds will cancel and our final answer will be in meters. So let's look at and see what the answer there. The answer there is 8.00 times 10 to the -7 meters as our answer. Next set of problems, and our next set of problems have to do with energy. So in these problems we are going to use E is equal to H times the frequency. And this first one's really easy because we are given the frequency, right? And we know Planck's constant, so we just have to multiply those together. So E here will be equal to Planck's constant, which is always 6.626 times 10 to the -34 joules seconds times 5.00 times 10 to the 14th 1 over s. So here seconds will cancel and our final answer will be in joules, which makes sense because it's an energy calculation. So when you're multiplying exponents, you add them together. So I'm going to estimate an answer and then we'll calculate it. So here we have 6.6, so I'll say 7 for that one, and times 5 is 35. So I'm going to say it's going to be around 35 times 10 to the -34 plus 14 which would give you -20, right? So 35 times 10 to the -20, or 3.5 times 10 to the -19 joules for my answer. So let me plug that into my calculator here and see, and I get 3.313 times 10 to the -19, pretty close to 3.5, so my estimate was close enough. And so now I'm going to think about significant figures. I have 1, 2, 3, 4 there. 1, 2, 3, 4 for the 6.626. And I've got 1, 2, 3 for my 5 times 10 to the 14th. So I'll need 3 significant figures in my answer. So 3.31 times 10 to the -19 joules will be my answer. Kind of a funny looking joules over there. I had a stray mark. All right. So now let's do our next problem, which is a little bit more complicated. Here we're solving again for energy, but instead of frequency, we're given wavelength. So it's a two-step problem. We'll have to change our wavelength into a frequency, and then we can multiply that by Planck's constant to get our answer. So here we have the wavelength problem. So we'll say frequency is equal to speed of light over our wavelength, which is 7.00 times 10 to the -7 meters. So here meters will cancel out and we'll get a frequency. Okay, so 3/7 equals to be 4.29 times 10 to the 14th 1 over S as our frequency. And then we'll plug it into our energy calculation. 6.626 times 10 to the -34 joules seconds there, times 4.29 times 10 to the 14th 1 over S. Okay. So let's do another estimate and calculation. So we got 7, approximately 7 times 4, which would give you 28, times 10 to the -20, or 2.8 times 10 to the -19. And if you do this, you actually get 2.84 is your answer. Remember, seconds cancel out, and joules will be your final answer for that problem. Okay, so this kind of concludes this recording where we talked about the wave nature or the dual nature of the electron. I'll have some example problems for you to work through and some solutions to look at as well, so you can practice these problems. Don't let these funny Greek letters throw you off or get you worried. It's pretty simple mathematically, and once you practice it, you will get it. In our next recording, we'll talk about a more complicated model of the atom, the quantum mechanical model, and I think you'll find that to be very interesting indeed, and we'll relate it to the Bohr model, which you might have had in maybe middle school, that planetary model of the atom. So thanks for your attention on this. Do your practice work and practice exam, and I look forward to seeing you in the next recording.